everyone, and especially to you grade 12s. I'm so glad that you could join us today as we start talking about differentiation. So this is our introduction to calculus. Calculus is a really exciting subject, and it is one of the big ones in maths. It's one that you really will get tested out on a lot in the exams, yes, but it's also one that has so many applications, and you always want to know, and certainly learners always ask, well, where will I use this? Where will I use this? Calculus is used all over the place. So even if you want to do a degree like engineering, or even if you're looking at something like a BCom accounting, there's even calculus in courses within those professional degrees. So it really comes up in so many places and has so many different applications. But obviously we need to start with the basics. So today's lesson, we're going to look at what is calculus, and then our main topic and focus for the remainder of the lesson will be differentiation by first principles. Okay, so I want you to start thinking about what calculus is, and really calculus is a subject of motion. So I don't want you to think statically and sort of linearly. I would like you to really widen and open your mind and think about how it can be applied. So maybe you started your calculus discussion in school starting with limits. Yes, that's where it seems to always start in the curriculum, but I want you to go deeper with the understanding that you have gained from school so far and draw on that knowledge to really take time to discuss what it is that calculus is all about. So I'm going to give you a few minutes to think about this. Look at the scenario that's on your screen, that's described on your screen. I'll give you 2 minutes to just think about this and come up with ideas, and we will go through this together. Okay, everyone, so we started today's lesson giving you an interesting question to ponder, to think about. Are you worried, right? So you're in a plane, you're doing some sightseeing, I don't know, maybe you're somewhere in Big Falls, or you're on some sort of a safari where you're seeing animals running around and that kind of thing, but you're doing sightseeing on this plane. And you notice the altimeter, and the altimeter is a device that measures your altitude, right? How high above the ground you are. This altimeter shows you a reading of 30 meters. Should you be worried? Well, should you be worried? And, I wish I could at this point hear what some of your responses are, but let's think about this, right? Now, if the plane's altitude is increasing, then probably not. Probably you shouldn't be worried because you're taking off. So you're increasing, your height will then increase, your altitude will increase. But then what if the plane is actually descending? So it's going down. Should you then be worried? Is that enough reason to worry? Because now you noticed, hang on, I'm 30 meters above, but I'm going down. Is that going to be a reason enough to worry? Well, it also depends because you don't know what's happening. Are you descending slowly? Are you descending quickly? If you are ascending, if you're going up, are you ascending quickly? Are you ascending slowly, right? Those kind of things we've got to think about when we ponder a question like this, right? So now you might be asking, well, what does this have to do with calculus? So really the point that I'm trying to make to you guys is that the plane's altitude alone isn't enough information to determine whether or not there's reason for concern, right? So if we just have the height above the ground, it's not enough information, okay? And this is where we can start thinking in terms of calculus, because calculus is all about measuring and describing change. So in the scenario where we're talking about the plane, knowing the plane's altitude alone at a particular moment in time is really not enough information for you to make any decisions. So it's equivalent to knowing a single point on the graph of a function. So for example, if I tell you the point 0.25 is on a graph, does that tell you anything? Does it tell you what the shape of the graph is, right? It's not the whole story, right? There's more to it. The question that comes next is this function, if we're talking about a function, is it going to increase? Is it going to decrease? And then even then, is the increase or decrease going to happen slowly or quickly? Will the function continue in that direction forever? Okay, and if you relate that to the story of the plane, those are the type of questions we needed to ask. What comes next? Okay, so let's take this back to calculus. So as I said, if we're talking about just the altitude of a plane, it's equivalent to just knowing a single point on the graph. That tells me nothing. That could be on any graph, right? What we need to know is the function going to increase? Is it going to decrease? And how quickly this is going to happen. So you can see I've drawn for you some graphs there where you can see what could be happening at that point, and then what's happening after the point is what we are interested in. Will the function continue in that direction forever, or will it change direction? Okay, so what you should see here is there's more to the story than just the function value. The function value, just a point on the graph, tells you nothing. We also need to look at the direction, how the function moves in that direction. And those kind of questions cannot be handled by algebra alone. Just with the tools you have so far, you cannot answer that question. We need a more powerful set of tools, and those tools come bundled in a package called calculus. Okay, so that's the big guy. That's what we're looking at today. That's the important concept for today's lesson. We're talking about calculus, the special set of tools that tells us so much more than just what a function value is. All right. Now, calculus is divided into two parts. We talk about differential calculus, which is based on rates of change, okay? And then we talk about integral calculus, which is based on adding up the effects of small changes. Now, integral calculus is not something that you are examined on in your normal grade 12 maths syllabus. For those of you who are watching and maybe you do AP maths, advanced program maths, you will deal with integral calculus. But for the core maths syllabus, we just look at differential calculus, all right? Then if we look at that part of calculus, which is differential calculus, we see that that is divided into two main forms, and that's a geometric form and a physical form. So geometrically, when we look at calculus, we're looking at finding slopes of curves, and we talk about slopes or tangents. So here we're looking at slopes of curves. And then physically, which we will get to much later on in this subject matter of calculus. Later on, we talk about velocities. So there's a physical interpretation and there's a geometric interpretation. And today we're going to be interested in the geometric interpretation, which is all about slopes of curves. All right. So hopefully what we've discussed so far has got you now interested in learning more about calculus, because obviously there's all these exciting things you can do with this section. However, it's all got to start somewhere, right? And generally where you start with in school is limits and then first principles. So in today's lesson, we're going to take this now to the core part of today's lesson, which is finding derivatives by first principles. As I said, you need to know that basics. You need to know those basics in order to do the really fun, exciting stuff later on. All right. So I'm going to give you 2 minutes to have a look at this, take this down and have a discussion. If you've got people around you, we'll come back and we'll do this together. All right, everyone, so we're going to talk now about finding the derivative by first principles. And so far what we've seen and what we're going to be looking at in today's lesson in differential calculus is the slope of a curve. So you all know how to find the slope of a straight line using that gradient. Y2 minus y1 over x2 minus x1. You're all familiar with that. It was pretty straightforward because it was on a straight line. But with calculus, we can extend that knowledge and we can say, well, we don't have to only find the gradient of a straight line. We can also find the gradient of a curve. So in today's lesson, that's what we're looking at. We're looking at the slope of a graph and the slopes of the tangent lines to the graph. All right, so we start by looking at the derivative function, and this is the formula that you would all be used to by now if you've been doing first principles. And this method is called, when you get this formula, it's called differentiation from first principles or using the definition. And I said to you, explain what each component represents. All right, so let's go through it one by one. All right. Let's start with f dash x and what that represents, or f prime x. So f prime x, it's really just a notation to denote, so the tick mark, you see that little tick there? That tells us that the function we're looking at is now a derivative function. So that tells us we are finding the derivative. All right. It also tells us that this function, f dash x, is obviously then related to some function, f of x, okay? And we call this Lagrange or Lagrange notation. And that's generally what you will see as f prime x. We read it as f prime x. It tells us we're taking the derivative of a function. Some of the other common notations that you will see while we are talking about this is you will see dy over dx, which means you're differentiating y with respect to x. All right, and remember, this is not a fraction. This tells me that I'm taking the derivative. Okay, so don't confuse that with fractions. So that's another notation you might see. You may also see y prime, which tells you you're deriving the function which is labeled as y, or g prime if you've called your function g. So those are the common ones that you use. There are other notations, but generally those three are the most common. All right. Now, f of x is something you're very familiar with because you've been working with it for a long time now. F of x is the function that you are dealing with. So that just tells you what the name of the function is. So for example, we could have maybe f of x is equal to x cubed minus x squared plus x minus 1. That would be an example of a function. All right. Now I want to look at this interesting word, limit. So this is the limit as h tends to 0. And let's talk a little bit about the limit and what it means. Okay. So we're looking at what limit means and what limit as h tends to 0. So really what it's saying is that we are approaching a certain value. So we're ignoring what's happening at that point and we're approaching that value from both sides. So we want to look at what happens on either side, as in this case, what happens when h approaches 0. So we're saying it's a value that may not even exist at that point, but we want to know what happens. So that's what, and you've already discussed limits before getting to calculus at school. That's really what you're talking about, is we're looking at what value the function approaches. Now here, when we introduce it into calculus, it takes on even a more special meaning, which we'll discuss just now when we look at that whole function of f prime x. All right, so the limit, what we said, is that it tells us what value your function is tending to, what value that it tends to. And the function may not even be defined it may not even be defined at that point, but the limit may exist. All right, so the answer gets closer and closer. So your answer is getting closer. It's closer and closer to a certain value. Okay. All right, so now let's look at f of x plus h. What does that mean? F of x plus h. All right. Now, this is a point on your graph. So just like f of x gives you a function value, f of x plus h also gives you a function value. So it's a point on the graph, that's h units away from x. All right. So for example, if you have any graph, let's just draw a parabola. All right, you've got a point, an x value that is at x units. So let's just say that's x. And then the other value, so the y value at that point, the function value will be f of x. And then we've got another point that's h units away from x, so this new point is x plus h, and f of x plus h tells me I'm looking for what the function value is at that point. So that's the function value at the point x plus h. All right, have we covered everything? Then the next thing we've got is if we take this now all together. All right, so let's erase that. If I take this whole thing together, the limit as h tends to 0 of f of x plus h minus f of x all over h. What you're really doing here is we're finding the gradient, because remember this formula is derived from your gradient formula. You can go through the derivation and see how it's derived. We're not going to do it in today's lesson, but by taking the point f of x plus h minus f of x all over the distance x plus h minus x, you can show the derivation of this formula. So really what we're doing when we look at the whole thing, the limit as h approaches 0 of f of x plus h minus f of x all over h, that really is telling me that I'm looking at the gradient at a point. How do I know it's at a point? It's because we're just taking the limit as h approaches 0, so it will give me the gradient at a point. So there I'm just looking at this section, so I'm not really looking at the f dash x part of it, but what does that mean? That's the gradient at a point. All right. And then if we look at the whole thing all together now, so we look at the whole thing, f prime x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. That whole thing all together, that formula, gives us the gradient of a curve, or it can tell us the slope of the tangent line anywhere on the function. Okay, so the tangent anywhere on a function, what the slope of that tangent will be, or it will give us the gradient of the function at any point. All right, so a derivative value is really telling you what direction the curve is going in. Okay, now I hope that you understand each of these individual parts, because we're going to need this formula when we are doing the remainder of today's lesson. I'm going to give you a little break now so that you can absorb everything we've done so far, and we'll come back and look at some questions where we apply the definition to first principles. Welcome back, everyone. So remember, in today's lesson we are discussing differentiation by first principles, and we've already discussed calculus and how important it is and what a powerful mathematical tool it is. All right. Now, before the break, I gave you the definition and the derivative of a function. We saw how it was written. We saw that f prime x is written as a limit as h approaches 0 of f of x plus h minus f of x all over h, and then we explained each of the little sections or the components that make up the definition. And just if you remember, what we were talking about is we were saying that overall the formula gives us the gradient of a function, or it gives us the gradient of a tangent anywhere on the function. If you were just looking at this little part of it here, f of x plus h minus f of x all over h, that just gives you your average gradient. So that's the average gradient, that's the gradient between 2 points. As soon as you add in the limit as h approaches 0, it then takes us to this. It's giving us the gradient of the tangent anywhere on the function. Okay, so with that in mind, I'd like you to now attempt a question. You can have a look at this question too, and I will give you, let's give you 2 minutes to do this. Okay, so in this question you were given a function f of x is equal to 4x squared and you had to find the derivative. Now remember, what the derivative is really giving you is the direction that the curve is going to go in at a particular spot. Okay, so let's have a look at how we will answer this. Find the derivative of f. Okay, so this should say f of x. Obviously, the prime shouldn't be there because as soon as we put the prime in, it means we're already deriving. So find the derivative of f of x is equal to 4x squared from first principles, and hence determine f prime 2 and explain what you have calculated. All right, so as soon as you see the words first principles, I know most learners get very happy because they know that they can put this formula down immediately. So it's f prime x is equal to the limit as h approaches naught of f of x plus h minus f of x all over h. And then learners will often say, well, must I write the limit down every time and as h approaches naught? Yes, you must. Because if you take that away, what are you finding? This is the average gradient. That's not what the derivative is, hey? It's not the average gradient. So therefore, if you leave the limit out, you are finding a completely different solution. So you need to put in the limit as h tends to naught each and every line. Okay, so f of x plus h. Now we're going to break this up and do it in a bit of a long way just because it's the first example we're doing today. So the one way you can approach this formula, instead of putting everything straight into the formula, is break it up and say, what are the different values? Okay, so for f of x, I know that I'm dealing with 4x squared. But what does f of x plus h mean? What am I doing there? So here what we're really doing is we're finding a function value. So say I gave you something like g of x is equal to 2x. And I then said to you, find the function value when x is equal to 2. What you would then do is you would replace 2 in the original function. You will replace x, with 2 in the original function. So it will become 2 times the value of x, which is also 2, and 2 times 2 will give me a function value of 4. So when you're finding f of x plus h, the principle is exactly the same. Wherever you see an x in the original function, you're going to replace the x value with your function value that you are looking for, which is x plus h. So we're going to replace our x value with x plus h to find out what f of x plus h is. So you see what I've done? Where there was an x, I now put in x plus h. But I see that x had to be squared, so therefore, if I'm just simply substituting x plus h into the original function, it should be 4 times x plus h squared. Okay, and then what you can do is you can first simplify that expression. So x plus h squared, that's the same as saying x plus h times x plus h. Okay, so we're squaring that binomial, we get x squared plus 2xh plus h squared, and that's just by finding the product of x plus h times x plus h. I then multiply the 4 into the bracket, and I get 4x squared plus 8xh plus 4h squared. Right, so I know what f of x plus h is, I know what f of x is. I can now then substitute back into my derivative definition. So therefore I can say, well, f prime x is going to be equal to the limit as h tends to naught of, remember it starts with f of x plus h, but we know that the overall value we saw is this that we've worked out. So therefore, in place of f of x plus h in my formula, I can put down what I've just worked out, which is 4x squared plus 8xh plus 4h squared minus f of x. That's the next part of the formula. It says minus f of x. So I need to now take away the original function. and then that's all over h. All right, we can do a bit of simplifying here. So again, yes, you do have to write down limit as h approaches naught. Let's subtract 4x squared minus 4x squared will cancel, and I'm left with, so if we simplify that, I'm just left with 8xh plus 4h squared all over h. And now a little hint here, guys. If you, at this step, after you've simplified, all right, so after you've simplified and added your like terms in that, at this point, you should only end up with terms that are attached to an h, so terms with h in it. All right? So if you look at 8x, h, it's got an h. 4h squared. Your terms at this point should all have an h in it, so that when you simplify, we can then tend h to naught. If you look at your what you get at this point after you've simplified your f of x plus h minus f of x, if you still have an x just there by itself without an h attached to it, then you've made a mistake. Okay, so at this point, and it's just a hint to help and guide you as you go through these steps, at this point of finding your derivative, there should be no lonely x's. I'll call them a lonely x because they're not joined to their h. Okay, so at this point you can see I've only got terms with h in it, which means I can factorize my numerator by taking h out as a common factor. So if I take h out, I divide through by h, I'm going to be left with 8x plus 4h. So I divide each and every term by the h that I've taken out as a common factor. The reason I do this, well, the h in the denominator can now be cancelled out, and I'm left with limit as h approaches 0 of 8x plus 4h. Now what happens here? At this point, you can see that you've got a single term with an h in it. So if I take the limit of that as h approaches 0, this entire expression here is going to tend to 0. Okay, so therefore all I'll be left with is just 8x. Okay, so a lot of people think of it almost as if I'm substituting h is equal to naught. It's not really what you're doing, but if it makes it easier for you to think of it that way, you can, but it's not, technically it's not correct. You're not putting h is equal to 0, you're actually tending 8x plus 4h to naught, and you're looking at what's happening, and you'll see that the 4h part of it will tend to 0. So all you'll be left with is just 8x. So what does this tell me? All right. We've taken the function f of x, we've found the derivative, and we get this value 8x. Well, that is now the gradient, this is the gradient of f of x is equal to 4x squared. So how that helps you, so we found the gradient of the curve. If I knew specific values for x, I could work out the gradient then at any point on the curve. All right. This also can be used to work out the slope of a tangent at any point on the curve. So the next part of the question said to you, well, find the derivative when x is equal to 2. Find f prime 2. And then you also had to explain what you have found. Well, you'll notice that we are dealing with the derivative function. So that means I'm looking at this function 8x. Because we know that the derivative of f of x is 8x. So if I want to find the derivative function value at the point 2, I simply substitute 2 in place of x, and I get 16. So what does the 16 tell me? It tells me that the gradient of your curve, so the gradient of f of x, at the point 2, so at 2, or the point 2, is 16. Or if you want to say it another way, the gradient of the tangent drawn to the graph f of x at the point 2 is also going to be, so the slope of the tangent is also going to be 16. All right. Okay, so we're going to now need to discuss a little bit more about finding the derivative by first principles, and hopefully you understand the logic that goes behind it now, all right? Now, sometimes those questions can get a little bit tricky to deal with, okay? And I know that a lot of times when learners are really not liking derivatives by first principles, it's when they're dealing with fractions, okay? So we're going to look at question 3. I'm going to give you some time now to take the question down, and then through the break, which we'll take just after this, you can then work out the answer to the first principles, finding the derivative by first principles. Okay, so this is question 3, and I'll give you 2 minutes to take this down. All right, everyone, so you've got this question down. I know it's going to take some time to do it, so I'm going to give you some time during this break, and then we'll come back and do it together. Welcome back, everyone. So a reminder, in today's lesson, we're talking about differentiation by first principles. We've looked at the logic and why it works, and we've also explained that there's a geometrical interpretation and a physical interpretation of differential calculus. Right now, we're looking at the geometrical interpretation, which is finding the slope of a function. Now, or finding the derivative, sorry, of a function. So just as the slope of a line tells you the direction the line is going, the derivative of a function tells you the direction the curve is going in. Okay, now this question here, calculate the derivative from first principles, and you're given a function p of x, is one that often gets learners tricked up, and I think it's because of the fraction. In fact, I know it's because of the fraction. All right, so let's first analyze what this question is saying. It says calculate dp dx. What does this mean? All right, the derivative, what this means is we're finding the derivative of p with respect to x. So it's the derivative that we are asked to find of p, derivative of your function p with respect to x. Another way we could have said this was to find p prime x, find the derivative of your function p. They said use first principles, so we know that we need to use the formula that we have by definition, and they've given you p of x as minus 1 over x, which would be a hyperbola. All right. So let's go through the mechanics of this. I'm looking for dp over dx. Remember, this is not a fraction, it's an operator. It tells us that we're looking for the derivative. So it's going to be the limit as h approaches naught, please don't use f because we're now dealing with the function p. So it's going to be the limit as h approaches naught of p of x plus h minus p of x all over h. All right, I'm not going to do this part separately. I'm going to do it all part of the same expression. If you want to, you can find p of x plus h on the side of your workbook and then put it in, but we're going to do it all together in one go. All right, so p of x plus h, that tells me that I need to, wherever there's an x, I need to replace that with x plus h in order to find that value. So my function p of x, remember, was minus 1 over x. So that means I'm going to replace the x in the denominator with x plus h. So therefore p of x plus h is going to look like this. It's going to be minus 1 over, not x, but I'm going to replace x with x plus h. All right? Minus p of x, be careful here, you need to use brackets. You are dealing with a negative expression, so it's going to be minus 1 over x, and that's all over h. All right, so we bring down, it's the limit. Remember I said to you, if you leave out limit as h tends to naught, you're no longer looking for the gradient at a point, you're looking for the average gradient. So please don't leave out limit. All right, so we end up with minus 1 over x plus h. Minus times a minus is a plus. Plus 1 over x all over h. So if you look at your numerator now, what you're dealing with is the subtraction of two fractions. Okay, so at this point, we're not even thinking about calculus. Here it's just algebra, right? So if I want to add the terms in the numerator, I need to find an LCD. My LCD is going to be a combination of x and x plus h. So therefore, my LCD in the numerator will be x times x plus h. If you're having problems with this, guys, this is really your fractions from grade 10. Okay, it's not calculus if you're struggling at this point. Okay, so my denominator in the numerator, if that makes sense, is going to be x times x plus h. And that means I need to times the minus 1, which is already over x plus h, by x. Plus, I need to multiply the 1 by the denominator x plus h. And then you notice this was all over h. So yes, I can write over h again, but I'm adding in extra steps because this divided by h, remember, division is just another way to write multiplication. So dividing by h is the same as saying multiply by 1 over h. So if I multiply 1 over h by my fraction that I have now, so if I'm saying this is what you're doing, you'll notice that that h will just join your denominator at the bottom. Okay, it's not included in your addition. It is just multiply by 1 over h. All right, so this is limits, and that's just so that we're not having a complex fraction where we have two different lines and 3 different steps of the fraction. All right, let's now add our like terms. I've got minus 1x plus x plus h. So minus 1x plus x is going to give me 0. All I'm left with in the numerator is h. In the denominator, I've got x times x plus h times by this other 1 over h. Do you see what I've said? And I've told you this, and to look for this clue that you're on the right step. Do you see, as soon as I've simplified my numerator, what happens? Every term with just the x cancels out, and all I'm left with is terms with an h. And it will always happen this way because you are tending the limit as h tends to naught, and the formula has been derived in a way that this will always be the case. All right? So h times 1 over h, those you can cancel out. So h divided by h is just 1. You're left with 1 over x squared plus xh because I multiply the x into the bracket. And then you see that we're saying the limit as h tends to naught. So at this point, if I tend the value of h to naught, this expression xh is also going to tend to 0. So therefore, all I'll be left with is 1 over x squared. And what this gives me is the gradient of the function minus 1 over x. All right, I hope that you all got to the same answer as well. I do know that it is a bit tricky when you're dealing with first principles and fractions. And for that very reason, I want to give you another one with the fraction. Okay, so it's not to torture you, it's to help you learn. Okay, so I want you to try question 4. I'll give you 2 minutes to take it down and to see how far you can get with this. All right, everyone, so let's get straight to this question because we don't have much time. You can take down the steps that I'm giving you, and hopefully what I'll do is I'll give you the answer and you can work towards that answer. So the derivative of f of x is going to be the limit as h tends to naught, and I'm going to go through this quite quickly. It's f of x plus h minus f of x all over h. So we're simply going to substitute into that formula. So it's going to be limit as h approaches naught of 1 over x plus h minus 2 minus 1 over x minus 2 all over h. All right, so that's going to be equal to, and then we find an LCD in the numerator. So it's limit as h approaches 0. My LCD is x plus h minus 2 times x minus 2. And then you have your when you add your like terms, you're going to end up with x minus 2 minus x plus h minus 2. This whole thing is multiplied by 1 over h. So this will be limit as h approaches naught. When you simplify this, so I'm giving you the tools so that you can do this yourself. When you simplify all of this, you end up with h over x plus h minus 2 x minus 2 times h. Your h's cancel and you end up with limit as h approaches 0 of 1 over, and you can test this out, x plus h minus 2 times x minus 2. So therefore you end up with the gradient being 1 over x minus 2 squared. Okay, so I really sped through that. Hopefully you got all of those steps down. So just a reminder that the derivative is the main tool that we use in differential calculus, and specifically a derivative is a function. It tells us about the rates of change or the slope of the tangent line. Until next time, cheers.